per slot. Now area of stator slot. How to calculate the area of stator slot? Approximate area per slot. So area of copper per slot divided by space factor. Now remember, area of copper per slot. So per slot conductors we have calculated ZSS. Just multiply it by using area of conductor in the stator side divided by space factor. Now this SF is new to you, space factor, where space factor is given by total conductors area divided by actual slot area, and the value of SF, it varies from 0.25 to 0.4. Now remember, we are selecting low value of SF for high voltage machines. Now why low value of SF is selected for high voltage machine? Because of some specific reason. As you all know, for high voltage, high insulation or more number of insulation is required. That's why we are selecting less value of SF. If you are selecting low value of SF for high voltage machine, then area per slot will increase. If you are decreasing the value of SF, as it is in inverse proportion, approximate area per slot will increase. So remember, for high voltage machine you must select low value of SF, and for low voltage machine you have to do the vice versa. This is the cross section of typical slot. Now as you see, this is the semi enclosed slot. Okay, so this WSS stands for width of stator slot and DSS stands for depth of stator slot. So remember this notation: WSS, width of stator slot, SS stands for stator slot, W stands for width, this D stands for depth, and SS stands for stator slot. Now to calculate the resistance of winding, here the winding round winding is shown. To calculate the resistance, you must know the length of mean turn of stator winding. So length of mean turn, LMTS, of stator winding is given by using following empirical formula. Now here we are using one empirical relation for this. LMTS is equal to 2L plus 2.3 tau plus 0.24 meter. Now you know the value of L. Yes, it is your stator core length. This is tau. Tau is nothing but your stator pole pitch plus 0.24. After that, stator winding resistance. If you know the value of LMTS by using this empirical formula, it is very easy to calculate stator winding resistance. The stator winding resistance per phase, RS, small rs, is given by rho L by A. But here L is your LMTS, that is length of mean turn of stator winding, divided by area of stator into number of stator turns per phase. This TR stands for number of stator turns per phase, where, as you all know, rho is the resistivity of conductor material, and generally we are preferring copper. The resistivity of copper is 0.21 ohm per meter per mm square. Now here, depth of stator core. This is the last point regarding the design of stator. So depth of stator core, we are using some notations for that. So DSS, depth of stator slot, DCS, depth of stator core behind the slot, and D0 or DO, outside diameter of the stator core. Now DSS, depth of stator slot. So by using this diagram, see here, this depth, this DSS is nothing but depth of stator slot. After that, DCS, depth of stator core behind the slot. Now this is your stator slot, and this one is the total length, which we are calling it as a DCS, which is depth of stator core behind the slot. So this total distance, it is nothing but your DCS. This is DSS. So always DCS is greater than DSS. Now flux through stator core is half the flux per pole. Now this is the assumptions we made. So if you assume the flux through the stator core is half the flux per pole, then area of cross section of the stator core is given by phi m by 2. Why? Because we have assumed it as a half divided by BCS. Now BCS stands for flux density in stator core. Now range of flux density in stator core is in between 1.2 to 1.4 Weber per meter square. Now remember this range 1.2 to 1.4 meter square, range of BCS. Now where that BCS is located? BCS is located in stator core. Now here this is your stator core. This overall area, this area is nothing but your stator core, and this the flux density in this area is given by your BCS, and the range of that is 1.2 to 1.4. Thus by using this formula you can calculate DCS, that is depth of stator core behind the slot, which is given by phi m by 2 BCS into Li. Li is nothing but your length of ion path. So this total ion path is nothing but your Li, and D0 or DO, outside diameter of your stator core, is given by D. This one is D, diameter of stator bore. After that 2 DSS. So this DSS plus this DSS. So 2 times DSS plus 2 times DCS. So this one is first DCS, second here DCS. So outside diameter of induction motor is calculated by using this formula. So DO plus D. So DO equal to D plus 2 times DSS plus 2 times DCS. Now here this completes the design of stator here. Thank you.